Yes, Mohammed, can we start?
Can you can start. Yep.
Okay, I start my presentation. Good afternoon, distinguished leaders, experts, and colleagues. First, hello.
Doctor, please let me to make brief introduction first.
Okay.
Okay. Hello, everyone. Thank you for joining us this webinar. My name is Ahmed Al-Jaber from GCC Lab. I'm Energy Consultation Department Head, and I will be the moderator for this webinar. As you know, the title for this webinar is the Research and the Practice of Demand Response Technologies in China. Actually, with the growing renewable energy integration, system fluctuating and seasonal peak load become more pronounced. Also, demand side response like the active load, energy storage, shifting load characteristic from rigid consumption to flexible, it is interactive behavior. So to address these changes, demand response technologies are essential. I'm pleased to introduce our speaker, Dr. John V. Chang. He is currently a professor senior engineer in China Electric Power Research Institute. Please join me in welcoming Dr. John V. To the virtual stage. Yes, Dr. John V, you can start from your side.
Okay, good afternoon, everyone. Can you see my slider? Yes. Okay, good afternoon, everyone. Distinguished leaders, experts, and colleagues. First, let me express my sincere appreciation to the organizer of the for the invitation. It is an honor to exchange my ideas with experts and engineers from across the industry. The topic of my presentation today is demand-side response technology exchange. Before moving to the technical content, allow me to briefly introduce myself. My name is Feixiang Gong. I'm a senior engineer at the China Electric Power Research Institute and have a PhD in engineering. My research focuses on demand-side response, virtual power plants, power big data analysis, and coordinate optimization on the demand side. Over the years, I have accumulated experience in both research and engineering practice. My report is organized into 4 parts. Part 1, background overview. I will discuss why demand-side response is critical at this stage, considering China's dual carbon goals and the rapid growth of renewables power, the challenges of extreme weather, and the evolving structure of demand-side loads. Part 2, innovation and application. I will highlight China's progress in both technology and market mechanisms, including AI-based forecasting and control. And part 3, demonstration. I will present practical cases from China like Jiangsu, Qingdao, Nantong, and Shanghai, covering millisecond level industry response, coordinated building load control, flexibility in the textile industry, and large-scale VPP operations, showing how demand response delivers measurable results. Part 4, future perspectives. I will look ahead to the next steps for demand-side response, focusing on standardization, market design, and cross-sector collaboration. Through these 4 sections, I hope to provide a comprehensive view of demand-side response and look forward to your comments and suggestions in the discussion. This session introduced the policy foundation for demand-side response. Internationally, frameworks such as the Paris Agreement the IEA DSM framework and IEC communication standards, ISO 50001, FERIC Order 745, and the EU Clean Energy Package provide important reference points. And in China, we have established a solid policy system, including the dual carbon targets, the administrative measures for demand-side management, and the Blue Book on new type power system development, and the technical guidelines for virtual power plants and response. Together, these international and national policies from the institutional backbone for advancing demand-side response. These slides emphasize China's dual carbon goals, peaking carbon emissions from by 2030 and achieving carbon neutrality by 2060. To reach this ambition, emissions from the power sector must be strictly controlled. In the new power system, supply-demand coordination is a defining feature. Flexible regulation of demand-side resources plays a crucial role both in accelerating the construction of this system and in supporting a green and low-carbon energy transition. Demand side is thus emerging as a key driver of the energy transition. China's renewable capacity has grown rapidly. According to the figures in the slides, from 2015 to 2024, wind and solar illustrations have risen continuously. This growth underpins the energy transition to and our dual carbon goals, but it also introduced significant operational challenges. Extreme weather events are also becoming more frequent. During heat waves in summer and cold spells in winter, peak loads rise quickly, increasing volatility and uncertainty. By 2024, peak demand under extreme weather conditions has far exceeded that of 7 years ago, placing greater pressure on system wrapping and balancing. Meanwhile, the demand-side load structure is undergoing a fundamental shift from rigid, purely consumptive loads to a peripheral with flexibility and prosumer characteristics. The large-scale integration of electric vehicles, distributed PV, and storage means that the demand side both consume power and under certain conditions support the grid. This transformation expands flexibility potential, but also increases control complexity. In short, tensions are growing among renewable integration, system security, and the effective mobilization of user-side flexibility. Against this backdrop, demand-side response has become indispensable. By combining technology and market mechanisms, demand-side response eases renewable accommodation pressure and provides new support for secure grid operation. With the background in place, I will now move to part 2, innovation and applications. In this section, I will focus on recent research progress and engineering practice, showing how demand response is being implemented through advances in both technology and market design. So, effective demand-side response relies on advanced forecasting and control. First, monitoring and identification. By developing intelligent terminals and adopting unified communication protocols, we can monitor flexible loads with high precision, giving operators accurate visibility of controllable resources. Second, forecasting. By introducing AI models such as deep reinforcement learning, we process both historic and real-time data to produce dynamic forecasts across multiple timescales. Compared with traditional linear or static models, these models better address renewable variability and load uncertainty. Third, control. With multi-agent coordination and 5G cloud edge architectures, minute-level response can be achieved. Demand-side resources can thus support not only intraday optimization, but also real-time dispatch, enhancing system flexibility and stability. Together, these capabilities are moving demand-side response from static management toward intelligent, dynamic, and real-time operation. The slide illustrates the closed loop from identification and forecasting to strategy generation and execution, forming a complete management circle for modern power system. This page introduces the digital pathway for demand-side resources, following the sensory, transmission, computing, control, route, and leveraging a cloud management edge and architecture with digital twins. The platform enables perception, communication, intelligent decision-making, real-time control, and cybersecurity for massive flexible resources. Across energy, spatial, and temporal dimensions, demand-side cluster can actively participate in multi-objectivities such as peak shaving, renewable integration, and ancillary services, transforming users from passive consumer into active participation in grid operations. Peak shaving and valley filling remain common application models. When reserve margins are tight in summer or winter, the system innatest demand response. Users, aggregators, and other market entities reduce or shift consumption according to dispatch requirement. The process typically includes single issuance by the grid, response by users or aggregators, monitoring and verification, and final settlement. The resource scope is abroad beyond the traditional industrial loads. It includes EV charging, building loads, and energy storage. For example, EV charging, given its inherent flexibility, can be deferred or scheduled to unlock significant regulation potential. The figure on the slide shows the roles of various entities: industry, buildings, transport, and storage in a coordinated network. Peak shaving today is not a simple curtailment. It is a market and technology-driven relocation of load across time and space to achieve accurate, flexible management. This slide highlights the construction of a unified information model. Demand-side response covers diverse resources such as centralized and decentralized air conditioning system, electric water heaters, boilers, distributed generations, EV, and energy storage. To enable seamless integration and coordination, we need standardized models. With unified modeling, different resources can be interconnected and coordinated, ensuring comprehensive coverage and stable regulation capability across the demand side. And China has made notable progress in both technology platforms and market mechanisms. On the technology side, State Grid have built intelligent demand response platforms and resource aggregation systems capable of real-time monitoring and dynamic control for millions of users. On the market side, ancillary service markets are opening to broader participation, increasing the activity of demand-side resources and enhancing market-based dispatch. So according to this slide, adjustable potential is distributed across the sectors. Industrial and commercial loads account for the largest share, followed by EV charging, distributed generation, and energy storage. This multi-sector participation provides a solid foundation for large-scale development. Effective side response depends on aggregation. Our cluster-based flexible control platforms support access and coordination of diverse loads and delivers three core functions. First, adjustable potential forecasting to assess future regulation capability in advance. Second, real-time strategy generation to ensure responsive and accurate control. Third, optimized dispatch recommendations to guide decision-making under complex operating conditions. These platforms has been developed in multi-cities, significantly improving flexibility and response speed. The system architecture and interface in the slide demonstrate that the platform is in practical operation and supports continuous skilled use. This slide illustrates the synergy between virtual power plants and electric vehicles in demand-side response. VPP aggregate distributed resources and flexible loads to shift demand, store energy, and support the grid. EVs through smart charging and V2G capabilities can return power to the system, helping balancing supply and demand. Together, VPP and EV create a more decentralized, flexible, and resilient power system, making them essential components of future demand-side response programs. This page shows a virtual power plant developed in a province from China with high wind penetration. The VPP aggregates and coordinates distributed resources and now operates at a significant scale. The total resources can reach 358 megawatts with a maximum regulating capability of 24 megawatts. It brings industrial and commercial loads, thermal storage, electric boilers, and energy storage into a unified control framework. The platform provides panoramic visibility and real-time supervision with advanced sensoring and communications. It supports millisecond level actions, enabling not only daily balancing, but also rapid response to coordinations. The data and the architecture indicated that the VPP have moved into application and are strengthening system stability in high renewable regions. This page presents the technology system for VPP built on a cloud edge end architecture and supported by a digital twin platform. VPP enable advanced control, intelligent perception, secure communications, and smart decision-making. With this framework, large-scale flexible resources can be monitored in real-time, aggregated and reliably dispatched. Demand-side resources can actively contribute to peak shaving, renewable integration, and ancillary services, strengthening both greater security and low carbon operations. This page outlines how VPP are evolving. First, multi-energy coordination and real-time response. VPP will increase coordinate electricity, heat, gas, and cooling to improve overall system efficiency. Second, unifying data standards and protocols. Standardization will remove interoperability barriers across generation, grid, load, and storage. Third, integration of AI and blockchain. AI will improve forecasting and decision-making. Blockchain will enhance transaction settlement and data integrating. Fourth, maturing market mechanisms. As ancillary services and carbon markets develop, VPP will expand roles in peak shaving, frequency regulation, reserves, and carbon reduction, becoming a key role of the new power system. According to the slide, the current maximum regulated power is 154 megawatts, and the maximum RAP rate is 15.7 megawatts per minute, equivalent to about 4.4%. These figures shows how, the VPP capability for fast and precise regulation in support of large-scale renewable integration. With the rapid growth of EV ownership, charging load increasingly affects the grid operation. In 2023, the national maximum EV charging load reached 18.44 gigawatt. About 2.96% of total load. EV charging has two defined attributes, concentration and flexibility. This means it can either intensify peak pressure or provide valuable flexibility for demand side. Pilot programs of ordinary charging in several cities have shown that by adjusting start times and charging power, evening peaks can be reduced and nighttime valleys filled. V2G allows EVs to act both loads and distribute energy resources, charging during valleys and discharging during peaks to support regulation, and in some cases, frequency control. In domestic pilots, when company employs V2G and peak shaving resource with good power tracking performance, another integrates V2G into a PV storage charging community model, where users benefit financially from discharging and have reduced electricity cost by 53. These results indicated that V2G enhance both greater flexibility and user value, and its role will grow as EV adoption increases. With the innovation and application landscape clarified, I will now move to part 3, demonstration. This case covers 86 precision manufacturing enterprises, including semiconductors and biomedicine, equipped with a rapid load control system capable of 0.05 second response. A gradual progressive current storage is adopted instead of a blanket curtailment, enabling file-gained staged adjustment that maintains system stability while minimizing production impact. In 2024, the system executed 41 responses with a maximum of single event reduction of 28.6 megawatts, ensuring system stability and generating considerable economic benefits and enterprises. The case demonstrates that demand-side response benefits both greater security and enterprise operations. Qingdao integrated 37 large commercial complexes, forming a 16.2 megawatts of controllable capacity for air conditioning loads, and an AI temperature model is employed, increasing set points 1 hour before the peak for pre-cooling and maintaining indoor temperature and 26 degrees during the peak. This approach preserves comfort while delivering meaningful reduction, confirming the significant potential of building loads under scientific modeling and control. On July 12, from 13 to 15, the program reduced the load by 41.3 megawatts, accounting for 9.2% of the day's peak value. Air conditions power consumption decreased by 15%. Economically, the program generated clear benefits for both users and the grid, avoiding additional investment needs. The result shows strong technical feasibility, economic rationality, and social value. For textile dyeing and finishing processes, a temperature time coupled control algorithm was developed. During heat preservation stages, power is reduced automatically. Steam wave of opening is linked to electricity price signals. A total of 142 enterprises have been integrated with 19.4 megawatts of adjustable load. In 2024, 67 transactions were completed, and each enterprise gained additional income, demonstrating clear economic benefits. This case illustrates that traditional manufacturing can also realize flexible through targeted technical measures. Shanghai has deployed a cloud edge and VPP architecture integrating distributed energy terminals, smart charging stations, and storage. The system collects data at 5-minute intervals and uses a 5G provider network for common dispatch, with AI generating dynamic response strategies. Regulation capacity has expanded from 15 megawatts to 200 megawatts. using multiple or multi-objective optimizations. The project simultaneously support greater security, user benefit, and carbon reductions. According to the slide, Midway Valley load increased by 120 megawatts. 85 megawatts was shifted from the evening peak, and the peak valley gap narrowed by 18%. Renewable utilization rose to 85%, and curtailment fell by 2 million kilowatts. The pilots employ a cloud edge and load management system that integrates concentrators, smart meters, and orderly charging across units, enabling 15-minute data collection through ARMI. Control comments are sent to user chargers to flexible adjust charging, support plug and play access, and provide app-based optimization suggestions. In practice, Jinan increased the number of chargers from 15 to 40 without capacity expansion, while new districts in Qingdao achieved zero expansion across 4 charging infrastructure. These results demonstrate that orderly charging can enhance greater flexibility and security while improving user charging efficiency. Having reviewed several demonstration cases, we now move to the final part of my presentation, future perspectives. In this section, I will discuss the future development of demand-side response and focusing on standardization, continued R&D, and the refinement of market mechanisms. On standardization, we must further refine the technical norms for platforms, equipment, and communications, and promote unified interface and third-party supervision. For VPP, continued R&D is needed in layered architectures, measurable response, secure communications, and market mechanisms, advancing distributed control and scheduling system. On the market side, demand-side trading should be optimized to increase credibility and user benefits with fair pay-for-service, cost-for-benefit mechanisms. Looking ahead, demand-side response will evolve from a regulatory tool into a cornerstone of the energy transition and the achievement of dual carbon goals. Here, I would like to share 3 recommendations. First, manage summer peak demand by applying smarter air conditioning control and demand-side response. We can ease great pressure during extreme heat waves. Second, integrate solar and storage. Developing VPP and distributed storage will further improve renewable utilization and enhance system stability. Third, plan for EV growth early. Proactively deploying smart charging and V2G pilots ensure that increased EV adoption strengths rather than burdens the grid. So today we reviewed the background of demand-side response, key technologies, AI-based and control, aggregation platforms, VPP, and also EV, and examine the demonstrations from Jiangsu, Qingdao, Nantong, and Jinan. Evidence from these projects shows that demand-side response has moved from concept to skilled practice with continued technical refinement and maturing market mechanisms. Demand-side response will play an increasingly important role in renewable integration, secure system operation, and the realization of our dual carbon goals. Thank you for your attention.
Okay, thank you, Dr. Fishang Gong, for this insight presentation. Now we are going to open the floor for discussion. So, dear audience, if you have any question, please feel free to type your question in the question and answer tab. I encourage everyone to engage and share your thoughts and to make the session interactive. So please feel free to write and type your question. So in the meantime, Dr. Fishang Gong, I have some questions here. The first one actually is, what is the role for the demand side response technology to play in the renewable integration and the grid regulation?
Okay, thank you for your question. So the demand-side response technology enables real-time monitoring and flexible control of user loads by smart terminals, standards protocols, and big data AI methods, allowing adjustment with seconds or minutes. For renewable integration, it shifts for or reduces consumption during low generation or greater stress, and increase usage during high renewable output, thus smoothing fluctuation and reducing reliance on conventional plants. For grid regulation combined with 5G and cloud edge and architecture, demand-side response resources can coordinate with the grid, enhancing adjustment capacity and reliability. This reduces the reserve cost and let users earn revenue by participation in spot and ancillary service markets. That's my answer.
Okay, thank you, Dr. Fishang Gong. Dear audience, again, if you have any question, please feel free to type your question, or you can ask directly direct your question directly to, you can enter and ask your question direct to the Dr. Fishang Gong.
Yeah, this is my email, and if you have any question, we can communicate by email in the future time.
Okay, Doctor, there is one more question regarding to the role of the electric vehicle in the demand side response. Yes, Doctor, I'm going to repeat my question. What is the role for the electric vehicles in the demand side response?
The VPP play in demand side response?
Yes.
Okay.
Electric vehicle specifically.
Oh, electric EV, yes. So electrical vehicles and V2G technology can act as flexible, controllable distributed resources. In demand-side response, EV can shift charging to renewable rich values and absorbing supply energy and or discharge during peak or emergency periods to support the grid. This slide shows shows that V2G combined with the VPP or load aggregation platforms can deliver second to minute scale response for peak shaving, frequency regulation, and reserves, boosting system flexibility while providing financial return for EV owners. This approach increases distributed renewable utilization and reduce system reserve cost. We think it will help both the grid and the EV owners, and it will be a great future, especially in China. Thank you.
Okay, thank you, Doctor. Now, just there is one message from the GCC, SIGRI GCC, regarding to the upcoming conference and exhibition, which will be held in Kuwait from 10 to 12 November. Just to invite you to attend and participate in that conference. Thank you, Dr. Fishan Gong, for your valuable insight and presentation. Thank you all for your participating today. We appreciate your time and engagement. Have a great day, and we look forward to seeing you in another webinar. Thank you so much. See you again.
Thank you.